And welcome back, ladies and gentlemen. After the excitement of the award ceremony of our Boost Up Competition 2021, we are now coming to the next highlight. And that is the Infineon Hackathon powered by EIT Manufacturing pitching session. For that, I'm going to invite Raphael Gattringer. He is responsible for startup corporation at Infineon Austria and is also a member of the global startup team at Infineon. Welcome, Raphael.
Yes, hello, back. I'm very pleased to be here. So this is actually now the goal of our whole Infineon Hackathon, this final hackathon session. I'm very proud and very thankful for all the teams that joined. We actually have participants from 9 different countries. So this is really amazing, 25 people who joined and 10 different teams. So I also want to introduce now or give a recap what happened. So we had 4 challenges. The first challenge was sound, where it was important to connect a Raspberry Pi to Infineon microphones and do some machine learning with it. In the second challenge, we had 3D. It was about a robot arm assembly where you can integrate a virtual time-of-flight camera. That was the original idea. Then we have biosensing. Biosensing is a new track together in collaboration with our partner MCI Innsbruck. What's also very interesting about this track is the first time we are offering Cypress hardware. Cypress is a semiconductor company Infineon acquired last year. And now internally, we're talking a lot with our employees that are mainly situated in the USA, and here a lot of fascinating development is going on. And this is the first hackathon here now where we are presenting this Cypress hardware. So I think this is also very interesting to watch what the outcome is going to be. And the fourth track is called circuit design and simulation. For us, this is also very, very interesting because the last challenge of this track, and it was an internal challenge, was 5 years ago. And we used this online hackathon, talked to our colleagues from circuit design and simulation with the Infineon Designer. You can use on our homepage to simulate and create circuits online to really first develop concepts of electronic circuits and then afterwards develop real hardware around it. So you can do some great online development beforehand. And so we were very happy that this also worked. Yeah, so actually, I think I asked this morning the teams how many hours they slept. So it was about between 4 hours and 7 hours. I didn't talk to everyone, so it could be that some people did not sleep at all, but perhaps they will tell us during the presentations or afterwards at the award ceremony. So I'm really keen on knowing how it was going. Actually, Hackathon started with a real highlight with the keynote from Stefan Rohringer, our deputy CTO of Infineon in Austria. And he's also now part of the jury, as well as the track owners that had a lot of work preparing these tracks that we can offer attractive challenges. And I also welcome Peter Kuhn and Teresa from AIT Manufacturing to the jury. And the jury will watch the presentations closely and then develop or suggest track winners in the end. What's for me very important is that we want to really support everyone. So for us, for sure, it's important or nice when you win a track, but at the same time, we really want to form a community. And perhaps you heard yesterday the panel with Sandra Stromberger about industry myths makers. So for us, it's really important supporting the community. And what we do with the makers with this support, we also extend to our startup engagement. So this is really something we really appreciate, and also the diversity that we see in the teams. We are a very diverse company, and we are a global player for sure. So we are really open to many different cultures and everyone is welcome. Yeah, so as I said, a small recap before we start. And I think we had a great start on Monday. As I said, it's the first hackathon during the pandemic, so to say, and we're very keen on the outcome and watching this and learning from this online experience. For sure, not everything is easy. So thank you for every team that joined. But we really tried to maximize the output. We also had morning sessions, like I already said, also yesterday, and interviews yesterday in the afternoon by my great colleague Markus, who did those interviews. And yeah, and we also, from some teams we heard more, from some teams we heard less, but suddenly you get an email with pictures about the work progress, and then you still know the team is still alive. And that's very great. Good. So then I will stop talking now. I think I already talked enough, and I would like to invite the first team. And every team has 5 minutes of pitching time, and then 5 additional minutes for possible questions. So the first team, and I'm really proud, is from India, from Abhijit and Deblina. And Abhijit, I would like to invite you now to grab the screen and present your pitch.
Hello everyone. So our team Iris, we came here with a project Autodesk. So our project is about building alternative way for industrial monitoring that does not require any immediate presence of any individual on that industrial site. So what does that mean is if one needs to monitor an industrial from a remote location or at your home, or if that person is not present right there on the industry, so they can remotely access and monitor the whole industry using by reading some sensor data and all. So the goal is to develop that economically viable communication module that can read the sensor data and transmit it over here for further process and storage. So what is the proposed design? So as you can see in the block diagram on the left side, like there are sensor nodes. We are calling it as sensor nodes that will be acquiring the sensor data and transmitting it over air over the LoRa network, right? And there will be a master module that will be receiving the sensor data and storing them into your computer as a graphical form, or storing the data in your computer in a database. So for if you need to track, like if something has went wrong somewhere in your industry, you can track it back by watching the data, by getting a graph of the data, like where something went wrong and what's wrong. So this is the total agenda of our project. Like we can, here are the sensor nodes. Like we will be showing you the sensor node circuit diagram right next to it. So it will be connected to the master module, and the sensors are going to connect it to each sensor nodes. So okay, so here is a circuit diagram of our sensor nodes that we are saying about that sensor node part. So this is a circuit diagram of our sensor node, that each sensor node has a microcontroller inside it, and the microcontroller is now controlling the. There are two multiplexers, two analog multiplexers are there. So on since we need to measure, there are various amount of sensors can be present at any particular location. So to measure various amount of number of sensors, we can we are using this analog multiplexer to multiplex many analog sensors into one ADC. And here also for to use digital inputs, we are again using one more multiplexer. Like there are two analog multiplexers are there. And with that, like there are sensors we know that uses the protocol of 4 to 20 milliampere protocol. So where the sensor data, the sensor readings are sent using the current, like 4 to 20 milliampere current values. So to do that, here are 5, 1, 2, 3, and 4, 5. There are 5 current loop support, like with voltage dropping resistor are there to measure the voltages using the ADCs, and the same is connected to the directly to the ADCs of the microcontroller. Like here, you can see PC. Yeah, here. And okay, so apart from this, like there is an instrumentation amplifier inbuilt within the circuit, which helps to measure resistive type voltages, like from a load cell example, or similar like those, where the voltage needs to be reading from bridge type sensor, so similar. And also it has an it is an amplifier, so it has a gain, adjustable gain, so you can measure the differential voltage with a gain. And finally, when these are the reading part, like they are reading the sensor data, and finally, when it gets reading and it sends the data using these sensor nodes, like using the LoRa modules, which acts as the transmitter of these packets or the data packets of the sensor values, and transmits it over the air. So yeah, like this part, like we are trying during this hackathon, like we got familiarized with the Infineon designer. We started designing the circuit. Like I have modeled those sensors, and I was saying that there are 4 to 20 milliampere those current loops of current sensors. So here are the five. There are five types of these. I have modeled them using these current sources. And here is the instrumentation amplifier and the XMC, this 1404 microcontroller. I am using that microcontroller. And okay, so here's the here is the analog switch or the analog multiplexer we are using. So okay, this simulation track, like I have simulated with some results. Like here it is. Here the simulation is like I am toggling the switches of the analog multiplexers, like from it is 000, 001. So it selecting the every. There are five sensors I am using and one instrumentation amplifier. So there are all total six types of sensors. It will be reading the data from total six types of sensors. So whenever the address is like 000, it is reading one sensor value. Whenever the address
Okay,
is
Abhijit, please come to an end. Thank you. The 5 minutes are over. Thank you.
Yeah. So by this way, like we have this transient response at the transient analysis, and here is the picture of our sensor node, which we predict to be like this, and here is the master module that is going to receive the data that's from the which is sent by the sensor nodes, and it's very simple. Like it's going to receive and transmit it over your computer via the UART communication part. It's very simple, and there needs some software that stores the data as in your database. Preferably here it's an HyperSQL DB, so it stores your data to your computer as a database. And here are the features, like it's low power, the long range, compatibility. There are 14 analog inputs per sensor nodes, 8 digital inputs, and with differential current loop, differential amplifier and current loop support, wide voltage range. And mainly the focus is on the sensor nodes. Like this is going to transmit, this is going to read the sensor data and transmit it. And
okay, Abhijit, sorry, we have to finish.
Right,
Just read one comment for each slide and then.
Yeah, like this is the tech stack. What we have used: LoRa, microcontroller, instrumentation amplifier, sensor interface, Wi-Fi. Yeah. So yeah, this is it. And further work, we are thinking into making a mobile application so that we can read the sensor data using your mobile. And yeah, thank you. This is it.
Okay, thank you. Thank you, Abhijit. Thank you for joining. Okay, then we have to move on very early, but I have a question. So how did you find the hackathon? What did you motivate you, and how was it using the tool? How does it help you for your project?
Okay, like this was really great. Like I got to know about the industry, like what simulation. Like yesterday when we were having a chat with Norbert, he is our mentor. So he was showing us like how to proceed, like the procedures, like what features like there are in the inside that Infineon designer. That was great. Like using that debugger, I was debugging a part, and to know about all these stuff and know about how to program. Like okay, the programming the microcontroller was a bit tricky, like that, and that took a chunk of time, but that was still that it was very fun and it was very uh, good to have this hackathon, and participation was really fruitful and it was lovely experience.
Okay, so Abhijit, thank you so much. Then I think we will continue with Mohammed. Abhijit, thank you so much, and here again in the evening and afternoon. So this shows reaching to India so under difficult circumstances. So thanks a lot for really being the first one to open this circuit design track. Now we have Mohammed here, and he is actually already experienced with Infineon hackathons. Last time we met in Villach, I think. And so he is actually a last-minute participant who joined us. So thanks a lot. I think you had like 24 hours. So, but as you are a PhD, you need less time. You're very skilled. So, Mohammed, I would say the floor is yours, and have fun presenting.
Hi, everyone. So this is Mohammed. I am from Budapest University. Actually, I did my PhD, so I joined the hackathon. Thank you, Rafael, to invite me here again. So I would like today to present my project based on, as my background in sound and voice, so I propose like audio compression amplifier, of course, for hearing aid. So you know that these people suffering from loud voice, and they are annoying for higher frequencies. So in this project, I would like to let's say clip these higher frequency by using some tools of Infineon. So let's first define the compression amplifier. So you can see that the gain compression so occurs when the input power of amplifier is increased to a level to reduce the gain of the amplifier, and of course will cause some non-linearity. So as the input power will be increased, then the amplifier gain should be decreased, and the amplifier goes into compression. So here we will focus on this area. And how can these help this hearing aid? So I mean, it turns down the volume when a signal becomes louder than a set level, and then it picks up when the signal drops below that level. So since the gain is desired on amplifier operation, so it's important to know also the limit of that signal. So there's like a simple equations of how can we set that signal. So based on the power input plus the gain that we need to set it previously, and then both of them should be equal to the power output. So as you can see from this figure, so I'm just here need to show you how can this project help these people. So here we have the input power, and this is the output power. So on the beginning, there's like a linearity when the input power is increased and the output power should be increased the same. But if we have, let's say, loudly signal, or for example, high frequency cause this loud level, then the compression amplifier should be here in order to cut or to clip this amount. So here, for example, if we can make differences between that linear line with the saturated one, we will see that we'll get like only 1 dB. So this point used as indicator showing the degree of nonlinearity of the amplifier. So what's the methodology in my project? So I need to receive a voice, let's say audio, sound, any kind of sound, even with the speech. Then there is like a microphone to get that sound, and after that input it to the compression amplifier. So I will first design the microphone. So because of the time limit, so I just design it quickly. I designed the microphone, and then I designed also the compression amplifier. And after that, I mixed both of them, and I will show you how can I do it. So this is the microphone. So I used the simple, let's say, circuit, and I run it, and it's done correctly. And this is the voltage of the microphone, and this is the output, and both of them are equal. And if we go to the amplifier, I mean the compression amplifier, it's also using the operation amplifier here and there, and with some of let's say resistance there, and we also it's the compression amplifier is alone, it's working, and this is the input and the output, and this is the levels of these boards that come out. And at the end, the idea is I need to combine these two components, but as I said, because the time limit, so it's not done yet, but hopefully in the near future I will work on it in order to input the signal from the microphone, and then I will compress that signal from the second component. So thank you very much.
Thank you, Mohammed. Perfect, just in time. And from my side, thank you that you joined the hackathon on last notice, so to say, short notice from my side. So thanks for showing the initiative. Let me just see. I have a question. You know, like last time you worked with hardware at the hackathon. This time you worked on this virtual basis from Iraq. Amazing. Thank you for joining. What was the experience, you know, working with hardware, now working on the virtual level?
Yeah, this is amazing actually, because you know that previously we work on only hardware. So we have like Raspberry, and there's like microphones. And when I came here, and you know that the COVID-19's the situation, so there is like again amazing software simulator tools by Infineon. So that's why it's a good idea to just combine these hardware with the software. And now with the software, this simulator, so we can see what we did and what we need to design before we, let's say, go to the hardware parts. So first of all, I like that software actually, and I found it's very useful for any designer that need to use the Infineon component in order to create such a beautiful device. Yeah.
So yeah, thank you for that response. We have now 2 questions. So what I see from the jury. So the first question is from Norbert Imlik, who organized this wonderful track. So he's asking you, Mohammed, when did you first start with Tina Infineon Designer?
When I start, sorry?
Working with the tool. When was the first time you started?
Yeah, yesterday night.
Okay, very clear and short question answer. Thank you so much. Yeah. And the second one from Stefan Rohringer. What is the innovation part here in your working with this?
Yeah, so
perhaps it's a tool. It could also be, you know.
Yeah, first of all, the idea is I need to help because I am doing the speech processing. So the idea I need to help the people who are suffering from high frequency sound. So these frequency affect their ears. So that's why I use these compression amplifier in order to clip these high frequencies. So this is the idea I needed to prevent it here. I need to invent it here, but. So when it's done, I think it will be good that these component of Infineon can do something good for people who are suffering from the high frequency loudly. That's some of that.
Okay, and we have an answer from Norbert. Amazing. So
okay, thank you.
I think you did a really wonderful job.
Thank you.
Okay, thank you also from Stefan Rohringer. And yeah, thanks so much. I think let's proceed. So Mohammed, thank you so much for joining, and all the best. Good. Then I see now I want to add something, and we had actually a third team, and I still want to count him as team. At the circuit design track, it was Tobias, and he was very interested. He worked 2 days In the end, he decided not to participate. But still, thank you, Tobias, for joining. I hope you had a nice experience, and you worked alone. Alone is always hard, so also respect for that. And as you worked 2 days, also we want to also see you as team and as someone who participated. So thanks a lot for that, Tobias from Germany. Okay, so now I see that the Statis is already in the waiting room. So Statis, I would like to invite you to present your solution, the team iBreath, and this now starts the soundtrack. So now we switch to machine learning and Raspberry Pi. So Statis, please go ahead.
Yeah, hello. My name is Tathis. So I welcome you to our presentation of our soundtrack project. It's for the Infineon Virtual Hackathon, obviously. On the left, you see Saria. She was our machine learning expert. And on the right, you see me. I was in charge of the hardware design. And I want to start this presentation with a quote. Innovation is any change, big or small, that makes a difference. And yeah, I am proud to present to you our solution. It's called iBreath. iBreath is a smart device that helps in the early detection of respiratory problems. So basically, we had the hardware from Infineon. We received the package, and I was actually able to build sort of a microphone enhancer with a membrane. And yeah, I know it doesn't look that pretty, but yeah, at least it works. Yeah, so this is the final product. You can see it here assembled. And it's basically a stethoscope. That's our main goal. And as my favorite writer, Simon Sinek, says in his latest book, you have to start with why. And my why happened back in February 2019, when my father passed away after an influenza infection that led to acute respiratory distress syndrome. And this is a syndrome that happens when you have a viral infection in your lungs. And basically the bronchi of the lungs close up in order to not transfer the virus to the rest of the body. But it's really a bigger problem. About 65 million people suffer from chronic obstructive pulmonary disease, or COPD in short. 334 million people suffer from asthma, which is the most common chronic disease of children. And finally, pneumonia kills millions of people annually and is a leading cause of death among children under the 5 years of age. In total, the leading causes of death are heart disease, obviously, stroke is second, but then if you see here, you see respiratory disease or COPD, lower respiratory infections, and lung cancer. And if you actually add these three, you can see that it's a much bigger problem than both these first causes. And yeah, this is a graph of the different infections that can happen on the respiratory system, and most of them can be actually diagnosed with our tool. Yeah, and of course, I don't have to mention that all our lives have been affected by the corona crisis, and it's a standard measure in hospitals that if oxygen levels drop below 95%, you have to intubate the patient, and our tool could help in the early diagnosis of such problems. So we took a respiratory database from Kaggle. Yeah, it consists of 920 sound files, a text file listing the diagnosis for its patient, and another one containing the demographic. And this is our model accuracy. As you can see, the accuracy is around 95%. This is another precision for its diagnosis and so on. It's an evaluation of our model. The hardware is obviously the Infineon microphone, the adapter, and the Raspberry Pi. And these two tiny stethoscope, if you will. So basically what we are suggesting is an application that would go in hand with this device. It would look like this. You would have to create your account. Then you would be able to choose your country, age, sex, activity level. If you have a chronic respiratory disease, and perhaps even your attending doctor's email. And then as you see here, there are three main functions. Here it says stethoscope recording. I don't know if that's visible, but that's what it says. So basically you would take a 30-second clip, 30-second recording of your lungs. Then you can analyze it, which would give you a diagnosis and an accuracy and precision of this diagnosis. And you can always share it and send it via email to your doctor. And here you can see different parts of the application. Of course, I wasn't able to build that, but you see the point. So our business model looks...
That is, we have to end
okay.
as soon as possible. So please just finish your slides with my final comments. Thank you.
Yeah, so you would send the audio file, perhaps even a heartbeat recording to your doctor, and he would then go on the diagnosis. So iBreath, we bring your doctor to your house. And now it's time for questions and feedback.
Thank you so much, Statis. So I also want to mention you're working with Saria. Saria is actually in Villach. You didn't meet, you met the first time at the hackathon, and you had the hardware, and Saria just participated virtually. So also congratulations for that. I'm looking now in the hackathon jury if there are any questions. So let me ask you, for you personally, what was the thing, what was motivating you most from this challenge?
I think what motivated me most is, I've been looking for a hackathon for the past 2 years. I was preferring, I would prefer it if the hackathon was on the weekends, because now I had to take vacation, but I'm really looking forward to the next one. I'm always looking for a new challenge.
So wonderful. We actually have now a few questions from Julian, who is our soundtrack leader. Did you use the code examples from GitHub? Question?
Yeah, I actually did. We had a problem with the Kaggle database came with its with sort of code. But I couldn't get the model to work yesterday, so I used the model that Julian had on GitHub, and I just adapted it to our specifications. And I also used the recording, the audio recording Python script.
And which parts of the shown idea did you implement?
Well, I implemented the recording of the sounds because I obviously had the hardware and I had to make sure that the sound is clear and analysis can be performed on it. And Saria did the machine learning model.
Okay, another question, were you able to collect sound samples and actually use them with your machine learning model?
Yeah, I did try it. Do you want me to do it now?
Or you just can answer it like this? It's just fine. We don't have more time.
I only did it once. I recorded my lung sounds once and passed it as an input to the model, and I got some results.
And final question, which problems did you face using our microphones and the example code?
Problems. I think the problems were mostly, yeah, you see, the thing I built, it wasn't so steady. So even the slightest move could induce sound and noise. And that actually messed up the recording. And I had to sort of, build around that. But other than that, I didn't have any problems. It was really, really easy.
Okay, that's your final words. Thank you so much. We have to move on. Thank you, Statis. Thank you, Saria. We're now at the 3D track. We will continue with the sound afterwards. So, Sebastian, I would like to open the floor to you, and you had this virtual 3D challenge, so please go ahead with your solution. Thank you.
Okay, thank you. We was the only team at the 3D track. Our team is here Yannick, Mohamed, and me, Sebastian. And we are all students from Stuttgart and are now at our master thesis here at Infineon in Villach. And we joined the 3D track and want to show you our project. So at first, our motivation was to make automatically 3D printer because we think this is the future. Last summer, we made a little project with a 3D printer and a little robot arm here. And he made a little pick and place action. You see the robot, he takes the blade here out of the robot 3D printer and put it here inside of our storage. And our idea is to make it more visible to identify the blade and afterwards to detect the object on the blade and put it down. So our motivation was the factory of the future with a 3D printer. The goal was pick and place action with automatically finished project and place it to a store, check if the parts are all right, and if not, the 3D printer updates his parameters and print again to make a good object. This is perfect for the industry for optimize the prototyping process for new products and make it easier to done in a fast time project. Herefore we have a simulation of a 3D arm, and we have to implement a time-of-flight sensor to our project. A time-of-flight sensor sends a light and detect it, and after the detection, he can calculate the time and know how far the point is away, and so you get a point cloud out of the sensor. You see it here. We integrate the camera, and the points are the detected points from the camera, and on the objects you see they're more nearer to the camera. Here's the picture from above from the view of the camera, and the big points are nearer and the small points are farther away from the spectator. And so we get a point cloud out of the JavaScript model here, and we integrate it to MATLAB. Here's the point cloud more visual. You see the yellow points are higher above than the blue ones. And you see a little bit here the objects, for example, the cylinder, here's the robot arm, here's a cube. And you see it here. This is the original picture of the scene. And we want to detect this object. For example, here we have a cylinder because we want to know where it is in the room to pick it with a robot and place it at a other place. So we only see here not a 3D element, we only see the top of the cylinder. So we reconstruct the cylinder so the robot knows where he can take it and place it later to another place. Herefore, we used MATLAB and the computer vision tool of MATLAB. And yeah, our further steps, our road is here, the roadmap. The first step we want to do afterwards is to combine the time-of-flight camera, our 3D printer, and our robot, and let them talk with an API, so we can interact real-time with all the three components. After this, we want to implement a pick-and-place algorithm who can pick a 3D printed object and place it to our store. Afterwards, we want to implement an object recognition with machine learning, who can compare the CAD file we create before the print, and afterwards, we can compare it with the real object and can look if it's fine or not fine, and if it's not fine, we can print it again. Yeah, this was our presentation. Thank you.
Yeah, so thank you, Sebastian. Thanks so much for contributing. It was also very special for us, this track, because you were the first one for you and your colleagues. You approached this topic. It was also very special for us because we collaborated with TOWIN, with Professor Schlund. So we are very happy with that. And also thanks to David, who really, I think, gave a lot of support.
Yeah, of course.
So thank you, David, for contributing support. So let me just see in the hackathon jury, they're still thinking about questions. Okay, that's fine. So you actually said in upfront, okay, this is new for you. So I said I encouraged you to to learn about a new topic. What was for you the interesting challenge in this challenge, so to say?
Yeah, we programmed the first time with JavaScript. We're normally programming with MATLAB or with Python. And it was very interesting because I never know that you can bring a project so easy to life, because with JavaScript, you only need your browser and you can run it there. You don't install anything. You only need one document and then you can run it from there. And yeah, and there's a cool toolbox where you can bring easy objects to life and show easy some stuff if you show it to some partners or other people.
Okay, and from David, the question, what was the most interesting but most challenging part, something where you said, oh, it's really hardcore?
I think the JavaScript, the whole code, because it was in a lot of files and we don't know where we get the information and where we have to go to insert it right at the right position. It was hard to analyze the program for us. Okay, very cool. So I would say congratulations for that. In the future, how do you think time of flight 3D cameras are going to be used, in technology? Because, for example, you also have radar, but where would you see this potential for time of flight? I think if you made little cameras, you can put it good in your smartphone or like this, and you can integrate it with some apps and make their cool stuff with it. Okay, wonderful. We have a question from Markus Hennecke, who organized this track together with Professor Schlund and David. Do you plan to continue after the hackathon? Yeah, I don't know, because we have buy a new 3D printer and have their new own projects to do. And I think this is our first step to do our own project with this new 3D printer. And maybe afterwards we continue it. Okay, and the final question, which characteristic of the printed parts do you want to inspect by machine learning?
And which parameters of the 3D printer would you like to chance to increase the quality, like the chance to increase the quality? So,
well, no, again, please.
yeah, I'll split it up. Which characteristic of the printed parts do you want to inspect by machine learning?
Yeah, we want to inspect the object later if it's fine. For example, you have some hanging elements. They're hanging in the air, and if you have no filament, you underfill under these elements, they get dropped down. And so we want to expect if there's, for example, more substructure needs to make the print better.
Okay, then I know there's the second question. Which parameters of the 3D printer would you like to, let's say, I think it's changed to increase the quality?
Yeah, it's the substructure you can use to make it more stable. Your object, maybe when it's hanging and you're printing in the air, it's come down, and sometimes you need more substructure to make it more stabilizing where in the at the time you print it.
Okay, so wonderful. Thanks a lot. And really from my side, congratulations for leading this track, pioneering this track in Infineon style. We pioneer stuff, so
yeah.
Thanks so much.
Thank you too.
You, and greetings to the team. Okay, so as you saw before, we had some internet connection issues. However, we will now continue with the biosensing track, and then at the end try to reconnect to the sound track. So sound issues there. But yeah, this is so audio people. We still have. We wanted to conclude the talk with Dylan and also Spartans of Machine. They might still pitch at the end if we can connect to them. But now let's open the biosensing track. I'm also very interested about the outcome, and we have already someone waiting, actually not far away, directly from Vienna, and that is Aaron and Martin. And I'm really happy to have you here. So Aaron, please start your presentation.
Okay, hello. I'm Aaron.
I'm Martin.
Martin is also here. We are the team Convivial Garden, or we call us like that. And we are actually 200 meters away from Raphael. We have a little presentation for you. And finally, we called it Danube in a Box, and it's about an interactive aquaponics system for classrooms. What is this? So we built a small-scale prototype. It's also behind us. We have there a complete ecosystem that is collected from the Danube, because we have the water from the Danube, the plants, not the top plants, but the water plants from the Danube. And we have also snails there. The idea of this is to have a research object that can be placed in classrooms, and it will help to understand the complexity of an ecosystem and maybe give an idea what it needs for sustainable actions for the future. Because we think that students are the caretakers of tomorrow, and so we have to address them. It's also a hands-on experience for students to understand ecosystems, because our idea is that in the biology lessons in school, they have this box and they can monitor it. So this is the prototype and the small scale prototype, and we also thought about a big scale prototype, and there we designed a 300-liter aquarium with different animals from the Danube and like 10 to 20 plants in there. Part of this, and we were also working on that, is the plant theremin. theremin is a music instrument. Part of this should be also an app for monitoring and control, and it's good to work together with Infineon because Infineon produces sensors and we need a lot of sensors. So we thought about temperature, water level. The water level can be done with the DSP we got in this hackathon, CO2, oxygen, pH, and nitrate. And here the last days we were working on the plant theremin, and therefore we connected the pads from the EEG you use normally to monitor the heart. We connected it to a plant, and it's working quite well. So the setup was the PSOC 5 from the hackathon set. The pressure sensor we thought about, but finally didn't manage to include it. And also we produced a sound generator on my laptop. But it's possible to do it also on a PSOC 5, but it was too less time to do it. So we use a different approach to use computer. And now I stopped the presentation for short. Zoom doesn't let me stop the presentation right now. Yes. Here in the back we have the plant, and if you touch it.
Sorry, there's some sound in the background. Perhaps you can stop it. Thanks.
Sorry. There was now a beep. Yes. If you touch it, then there's different sounds. I don't know if it's working that you can hear. But there below it we have the pads, and if you touch the plant, it's generating sound.
Okay, so it's from the prototype. Okay.
Now the live sound from the prototype. Now we can go back.
Okay, I think we heard it. I think you can stop the sounds now.
Okay, I stop it now. Yeah. Okay. I'm really sorry. Here now. The next thing is next steps and what we have learned. Actually, I was participating also in the Industry Meets Maker meeting like 2 weeks ago. And there I was in a track where the Wirtschaftsagentur Wien was asking for educational objects that can teach what's happening at the moment in the market in Austria and to how innovation is happening in Austria. And we thought that we put this Aquaponic Danube box in their project to teach the students that are visiting in September there. And we also thought that maybe we can collaborate with the National Park Donauauen to develop the accompanying educative materials, for example, describing which animals are living there next to Vienna. Yes, then what we've learned is, what was new for us is that programmable schematics on a chip. So you don't have to actually connect the analog things on a breadboard or on a PCB, but you can just program it. And this was new for us, and this was really, really funny to work with. Then another part was that you can build an aquarium with wood and epoxy that is working. It was also funny to see it. And also, we are happy that the snails we have in our aquarium are still living after 3 days or 2 days. And also we had a good teamwork here in the the team together with Martin. And the hard things we learned was the software development for hardware is mostly done in C and Windows. So we had the most difficulties in these things because we normally don't work with Windows and we don't work with C. So this was new, but we managed to get it working. So quite happy about this outcome. And then finally we have the contact. And that's it.
Thank you so much, Aaron and Martin. Let me just see, there's a question here already from Markus Hennecke. What kind of information can one deduce from the potential difference on the plant?
The first thing we learned is that the plant has like a sinus inside the plant. It's always circulating between 2 points all the time, and if you touch it, it changes the range in between it circulates. So what we can learn is that if you touch a plant, the plant actually it has an effect on the plant, and this was really interesting to see. And also, if you see it as a curve, there are some spikes occurring, and if you touch it, they are occurring way more often than if the plant is just like that. So we thought if you put it in this educational context again, it raises the sensibility that the plant has also, that if you even touch a plant, it has an impact. So the plant is well connected with the environment.
And did you know this before the hackathon, or did you explore this during the hackathon? Because I won't know it, so it's really fascinating for me.
I knew that there are some experiments like that, and there's also a product which does it since like 5 years, but I didn't have it in hand. And for me, the interesting part was to how which data comes out of the plant and how to interpret it, because this was also most of the time that we had to write an algorithm that because if you just connect the data to the sound, it's nonsense and it's loud. If you have to write an algorithm to filter the interesting parts out of it.
Okay, Marcus wrote, because we have now here phenomena, but we don't know, or you might know where it comes from, but Marcus asked, did this happen to be a 50 Hertz sinusoid?
It's I don't know the altitude or the hertz of the sinus, but actually what we do is we influence with the conductivity, we influence a sinus wave. So we generate a wave and the plant is modifying the wave. So yeah, yes, it's somehow, because if you just take the values, it's ranging between minus 6,000 and plus 6,000, and we had to map it somewhere that we can hear it. So we added the values of the plant to a sinus wave that we produce.
Okay, so much to learn. I'm a great fan. And now I welcome Dylan.
Hello, we are Identify. We're a group of Indonesian students, and we're a group of 5. Our names are Azhar, Dennis, Dylan, Jessica, and Oscar. I'm Dylan, and I will be presenting our project today. And so the name of our project is Identify. A bit of an introduction. The ID here stands for Indonesia, and the color red and white is actually the flag of Indonesia, where we come from. And so here again is a very quick introduction to who we are. We study electrical engineering, and some of us study informatics as well. And so our project is essentially, we are implementing machine learning into the Raspberry Pi. And so the motivation behind this project is that we want to know sometimes what's happening in our house when we're not home, or maybe when we're busy using noise canceling earphones, we want to know what's happening around us. And so we're using audio input from the Raspberry Pi to process all this information and then return the output as in an interface form so that we can see what's happening from the sounds happening around us. And so here are our targets, more or less. We want to be able to make an interface through which we can securely detect suspicious activities in your house through sound. It's accessible via an interface that you can hold in your hand, and that can be brought with you anywhere, and you can access the information mobile from anywhere. And so that's it. And as for the next part, this is a brief introduction of the system that we're introducing into the Raspberry Pi. So the microphone from Infineon which is already attached to the Raspberry Pi, will first detect sound, and this sound data that the Raspberry Pi receives will then be transferred into the machine learning model, which we have installed and implemented into the Raspberry Pi that we have. And so the model that's already in the Pi will then try to process the data, and then it will output what it thinks the sound is. And this result will be then outputted into a dashboard, which will be available through a website. And so the machine learning model is based on available data sets that we have so far. And the concept is that we can keep on improving it by adding more and more data as machine learning is. And of course, we can add more classification. In order to clarify a bit what we mean by classification of sounds here, let's say, for example, that you have a dog barking right outside of your house. That might be an intruder. So the Raspberry Pi then catches the sound and tells you via the interface, via the browser that, hey, there's a sound outside. It might be an intruder. You might want to check that out. And so that's how we implemented the machine learning model into it. And this machine learning model can be expanded into multiple categories. And so how will this be controlled, all of this? And so we're controlling it through speech recognition that comes with the Raspberry Pi as well. And so these are some of the recognized sounds by our mechanism. So a quick brief recap of the mechanism is, essentially speaking, we're implementing the Raspberry Pi to be able to recognize sounds surrounding the Raspberry Pi and classify it into a class of sounds. And these are the classes of sounds so far recognized by the Raspberry Pi, which include dog bark, air conditioner, car horn, and etc. And so real quick, see how it works. So as a start, I will now first show you what it actually looks like, what the interface looks like. And so this is the interface that we have implemented. Whenever the Raspberry Pi gets input of data, the information here will be changed according to what data it's getting and what it's being asked to do. So when you ask it to increase the volume or decrease the volume, the sound system, the writings here on the sound system will change accordingly. And so as next, I will now show you the live demonstration of the Raspberry Pi that we already have. So as you can see here, this is the Raspberry Pi that we have, and to the side we have the console going on as well. The console is recurringly getting information from its surrounding using the Infineon microphones, and we'll give a very, very quick demonstration right here. So let's say there is also a system where it needs a command in order to actually be executed in the first place. So the command call here is OK Google. We're using OK Google because it's something that we're very familiar with. So let's say, for first things first, OK Google, turn the lights off. And so, okay, let's restart that real quick. I think it didn't catch the OK Google part. OK Google, turn the lights off. OK Google, turn the lights off. Okay, and as you can see behind me, the lights have been turned off, and that's activated from the OK Google. And if we want to turn it back on, okay, Google, turn the lights on. And so now the lights are turned back on, as you can see right here. And so that's how it works more or less. And apart from that, we can also identify the sounds. As I've said, this is actually the main functionality of our project. Okay, Google, identify. Okay, Google, identify. Okay, Google, identify. And now we've played a video, a sound recording of car horns, and as you can see in the screen right here, it's actually detected the sound as car horn sounds, and that's the machine learning model inside of a Raspberry Pi actually working and processing the data in order to get the information out of it and specify it into a certain class. And so as for a very last feature that we have here implemented as well, it's okay, Google, rotate colors. Okay, Google, rotate colors. Okay, Google, rotate colors. And as you can see here, the LED strips in our room right now is currently rotating colors through the spectrum. And that's the implementation that we have done so far for the Raspberry Pi. Thank you very much for watching. If you have any questions, you can ask them.
Okay, Dylan, thank you for explaining. Okay, thank you so much. Let me just check the jury chat. Perhaps we can also use the chats, the questions by the other group. Did you use the code examples from GitHub?
Yes, we have some code samples from GitHub. That's right.
Okay, which parts of the shown idea did you implement? Or okay, we already saw something.
So
yeah.
we used a bit of the data set that's we use some data sets that's already available online for the sound for the machine learning model training. And after inputting the machine learning model sets, we have a model which we can actually use to classify the sounds. And as from Infineon, we actually use the GitHub repository from Infineon to be able to capture the sounds using the Infineon microphone.
Okay, and which software framework did you use to implement your classification?
We used TensorFlow and Keras for that, the machine learning part of it.
Okay, and the final question: which problems did you face using our microphone and the example code?
We faced a lot of problems with the sensitivity, as the microphone was sometimes a bit too sensitive, and it did capture some things that we didn't really want to capture.
Okay, so we see that our microphones are very sensitive, but for sure, with the perfect system, I'm sure they're of great help. Okay, so we have to move on. I'm very happy that the reconnection managed was okay. So thank you, Dylan, and greetings, and see you in the evening. Greetings to the team. And next, we will still finish the soundtrack, and in the end have the biosensing also completion. So I would like to welcome Kumar, and the floor is yours.
So we are the Spartans of machines. We are comprised of 3 students from TU Chemnitz, Germany, and we all are writing master thesis right now. And we are Kumar Manas, Raj Pawar, and Saras Sesar. Unfortunately, our hardware prototype is not ready yet due to soldering iron missings and other items which we have ordered from the Amazon could not reach to us yet. So only software prototype is ready for us. So first about our what we wanted to do. So we wanted to classify the sound of an image based on what that image sound is. For example, is this a sound of a car? Is this a sound of a human being? Or for example, we can also use this if we have the customized data set, that is this a sound of bird X, bird Y, bird Z. So we can classify some rare bird species as well. So just like Alexa listens to your voice and they follow your command, they are able to do that because they can recognize what you are telling. So for this application of Hackathon, we have used urban sound dataset. This is the one of the most widely used dataset, and we trained our TensorFlow and Keras-based model. And later, I have deployed it on the edge devices, which is Raspberry Pi here. As you can see on the screen, when sound speaks, then our Seal2Go captures those things, and then Raspberry Pi, on which models is deployed, do the processing of that sound, and they can give the value that what does this sound is. So this is the basic setup where we just listen, pre-process using the microphone, and then get the value. So how we did it? So first we did a full precision or default training methodology on the TensorFlow and Keras, which use 32-bit full precision floating point. And then there are two ways of convert those models so that they are not too heavy for our Raspberry Pi, because we are concerned with the limited resources. So we can quantize it. Either we can do 16-bit, 8-bit, or 1-bit. TensorFlow Lite have the inbuilt capability to convert our model. We just have with a couple of lines of code, we can just convert .h5 or model file into TF Lite, and we can deploy those TF Lite new H5 file, which is come after TF Lite processing on our Raspberry Pi, and you can use that. But there are other ways of doing that. That comes from a past research project in which I converted whole model by myself into 8-bit and 1-bit. 1-bit are highly compressed model. There is some trade-off between, you do some trade-off, because if you reduce the precision of model, all the back propagation and gradient descent of the model does not work properly, because they are very less value or to move around, so accuracy decreases. So I tried two ways. One, to directly convert my full precision model using the TF Lite, that's called 8-bit quantization. Another, based on my past project, I just converted it into 8-bit and 1-bit. And based on that, we found that accuracy decreases by 5 to 7%, but that causes so much reduction in parameter that it's very efficient to deploy on the, not only on the Raspberry Pi, we can deploy them on the microcontroller as well. Since our hardware prototype was not ready, so we have more time to work on the software part. And based on that, I can show this all the result. We have used the model. If we use the 1-bit model, it's just 17.14 MB of size instead of a 32-bit model, which is 546 MB. And the reason is that our model can convert a lot of multi-planned accumulate MAC operations from 32-bit to 1-bit. And that's the reason model is so less heavy for the RAM or memory constraint device that we can deploy it for the low power and low cost devices. And now coming to why we are planning to use this on the edge devices. One is that privacy of sound. For example, many doctors try to classify based on your sound that you have a flu or if you have some different kind of disease, or there are many areas where privacy is much more required. So we required S platform for that. And another thing is that model can be used in an online fashion. If you have the edge devices and you can deploy it many places, you don't need GPU cluster to train because your model is already trained on something and you just use it on the go. They are cost effective. And since if you have the new kind of training data, new kind of model you want to deploy, just like from the Raspberry Pi, we can do headless server and all those things. We can deploy models online on the edge devices. And also, just like I haven't tested the Seal2Go, but as from the other participant, it is quite sensitive to noise. So it's like if you are more sensitive, you can capture the annotations of voice more precisely, and that helps model to clarify or classify the sound in a proper way, especially in those classes in which the difference between one sound and another sound is almost negligible. So some problems while implementation. First is that while converting model for the edge devices, there are a lot of different kind of problems happens in terms of the, for example, the usual loss functions and other functions are not working properly, especially for the, if we convert for the edge devices, especially if we write code by ourselves for conversion it into the 8-bit or 1-bit compared to TF Lite. Another problem is that software compatibility version, because many software versions, for example, TensorFlow, associated library, sometimes don't work. For example, we have used Librosa and they don't work that version same on the laptop and the Raspberry Pi, so we have to downgrade. And there is something called a speed and accuracy trade-off, because if you convert your model into TF Lite or low precision, it decreases your accuracy, and that you have to decide you want more accuracy or more a small model. And another problem we found that vanishing gradient problem, in which that if we remove the precision value from 32-bit to 8-bit like TF Lite do, gradient descent does not happen properly. And that's why the reason people don't use a small TF Lite-like model for training. They just train on the full precision and deploy on the model so that back propagation can happen properly. And but disadvantage is that if we cannot train model on our Raspberry Pi, then we have to retrain on the laptop and transfer those model to the Raspberry Pi. That's the one of the problem in which vanishing gradient problem can be solved, that you have to train your model each and every time. And now coming to future use cases is that we can do for medical sound classification, bird and real animal voice. If we have, say, for biologists or some environmentalists want to know if there are some kind of bird still present in this area, they can deploy Raspberry Pi with Seal2Go, and if they listen to those sound, they can make track of those things that yes, there are presence of this kind of animals. And one interesting use case I found that it's like a lot of machines have different kind of noise once they stop working properly. So based on those classification, if we can train our model on the good machine noise or working machine noise compared to problematic machine, we can have the clear indication that machine is not working properly. And yeah, there are other use cases as well. And then, yeah, thank you. And I'm open for questions now, especially from the software standpoint.
Okay, thank you, Kumar.
Yeah.
I didn't want to interrupt you because you were actually already answering questions that could have been anticipated from the jury. So thanks for answering that in advance. I'm now looking to the jury if there are any new questions. Otherwise, just ask the standard ones. Did you use code examples from GitHub?
Yeah, some samples I used from my past research project in which I worked in the university for my own credit point, in which I have to convert models into 1-bit, 8-bit, and how does vanishing gradient problems and all these were solved. But yeah, those were mostly my problem. And we have used dataset pre-processing from the GitHub, and dataset is already in the public domain, how to pre-process that thing. So we have used that too from the GitHub. And yeah, and code base was on TensorFlow and Keras.
Okay, so I see Julian is typing. So just I think a final question is dropping in. We still have some time. After you, there are still 2 teams. The questions do not really work because the team didn't work. Okay, you didn't really were so engaged. Okay, in the hardware. Okay, now I understand it.
My hardware is just this much ready. I have put, if you can see, put everything on the thing, but I could not connect due to the absence of jumpers, wire, and soldering iron. But yeah, basic model is ready. I think if I get by today, I will try to work for my own hobby project.
Wonderful.
Complete.
So I hope you can use it somehow for your other project.
Yeah.
Okay, Kumar, thanks so much.
Yeah.
Greetings to the team. Greetings from Vienna to Dresden. And thank you. And let's move on to the next team. Yeah. Thank you, Kumar. Thank you. Greetings. Bye-bye. So I would like to introduce Sergey. Sergey is a very experienced, I don't want to say Infineon engineer, but especially a Infineon Hackathon veteran. He won already 2 tracks, and but he decided to join again. He was invited, especially invited because he already won a track. So once you win a track, you're always invited to further events. So Sergey, we are returning now to the biosensing track, to the final 2 pitches. I would say I don't want to talk too much. The floor is yours. Go ahead. Thank you.
Hi, thank you for introduction. Hi, everyone. I will speak on behalf of our team, Midnight Programmers. As Rafael already said, we participated a couple of times, and it's engagement experience. We want to do it even if it's online. So we are here again. This time we started with biosensing track, which was a new one. So it's something like to challenge ourselves, because we have not much experience in biosensing so far, and also with Cypress equipment. So I want to tell you a bit of story, the background story, why we did there. In general, there is like a world trend to some kind of smart tools. And one of the smart tools is like smart glasses, what is like might seen as AR glasses, would be a more correct way to say it, which will help you in your daily life, something like this vision we have often here and there. In reality, this looks like this. Maybe you know this is a Google IR glasses, which was not really that successful, and it's kind of a failure. But the thing is that this like world is changing, is turning on its head, because there's like big players coming into the game, and there are also really nice technical solutions which will allow us to have real kind of a proper smart glasses, AR glasses experience, like on the first picture. The problem with these solutions is they kind of address the image part, which is obviously the most complicated, but it do not, let's say, concentrate much on the hardware input, so like a hardware machine interface, human machine interface, sorry. So, for example, these prototypes typically operate as a sensor pad, so you have to kind of slide something whatsoever. So we thought it's like to have this package complete, and like to think and have a vision of something I personally want, and like we want to have now. We address one of the things which is missing is like a proper interface to it, and we think the proper interface is like brain-computer interface. However, there's one problem. So if you think about like brain-computer interface, and you like think about EEG, it's typically some big thing which consists of like 30, 50 electrodes, and it's like actually a cap you have to put on your head with some gel on top. And yeah, very nasty thing then to clean up afterwards. So to be with the concept of smart glasses and like smart device you can use daily, it has to be modified. So I have a very simple sketch of a human head, and like our idea that we can use only the electrodes at the back. So at the back of the head, where the frame of the glasses will touch your head, you have also a skin which free from any hairs. So it's very nice contact point. And we like start with this idea to go in the direction of EEG, or like brain-computer interface for like future smart glasses application, which is the main motivation, but with very, very reduced amount of inputs. So instead of this full cap, we want to have it like practically, would be something like 4 or 6 electrodes, where I put also the colors. So this like a sampling electrodes, and then there's like a reference or ground, you might say. And then other way around. So you have like 6 electrodes without cap and technically without gel. So that's something you would like to wear every day. So that was our initial motivation, and where we like the idea where we counted this hackathon to this biosensing track. So now coming back to like real things, we have this idea concept in mind. So we implemented the thing in PSOC device. So we have this measurement system. We tried different options with and without like gains and so on. But it's kind of one of the more stable prototypes, where you have a automatic multiplexing of like 4 sensing channel and 2 reference channels. And then these things is communicated via USB, via UART bridge to MATLAB on the PC, where you have a data processing and potentially can also like extract data, save, and use for the machine learning. So that was the initial idea. And when we done a first run, we realized that, we wouldn't be able to make it. There is not enough sensitivity of such system to measure like microvolts levels we need for the brain-computer interface. So we will ended up, okay, let's go to EEG. We have the system in there, so we just modify like we attach the electrodes, and then it should work. So that's how the real EEG looks like of a person, and then how our EEG looks like. So if you are not a doctor, you might think it's okay. If you are somehow have some vision on the EEG, you will understand it's completely garbage. So we're completely lost in the noise here. And that's something, let's say, for us, it was a clear takeaway that we have to do a proper analog front end. The microcontroller cannot pull in on its own. So another picture like of a test bench I already mentioned our meetup that I don't have like a proper place at home. So actually I was working on the floor, especially last hours. And yeah, here's our PSOC development board. And on one laptop, I developed the code. And then on the other one, I had a MATLAB, and I was able to run the things and test it. And then, of course, those wires doesn't go somewhere, that goes to the body. So you see a couple of here in the hand and also a couple of them on the chest. The results, 40 hours, we survived. We have no losses in the human stuff. 9 hours of sleep, at least for me personally, like was 5 hours in the first day, was 4 hours today in the night. We had 2 hardware setups. So I showed a picture of my setup. That also Volodymyr had also a setup on his side. And then we have a full virtual collaboration. So like in total was about 11 hours online in Skype with Volodymyr and Georgi. Georgi was mainly working on the MATLAB part. Volodymyr also was working on the hardware. Yeah, so we developed like the outcome, the main outcome. We have the setup for kind of biosensing ready. EEG, well, maybe ECG, EMG, yes, ECG, maybe EEG, for sure not that. But we have a measurement in the PSOC, we have a communication, we have post-processing MATLAB established, so it's really a framework ready. To make it running, we need the analog front end, so that would be like one of the next steps. And personally to me, this topic is still very interesting, very promising, and we'll definitely follow up. So we'll see us on the Kickstarter. Thank you.
Thank you, Sergey, for your wonderful presentation. You already were part of the interviews yesterday, and I think also today you will give a comment on the hackathon. So please, everyone who's watching, also watch our interviews later on that will be conducted by Markus. So let me just check the forum. I see already someone is typing. Perhaps what was the most interesting part for you? Question from myself.
Well, is to touch a world which was not known to you before. So for us, for our team, we had not much background, or any background in biosensing at all. So of course, everybody here was ECG, EEG is, but nobody actually like does it like hands-on, or you do it very rarely. So that was really new to us, and a lot of learnings on that, seriously. And also it was really a new opening for the PSOC family. So the former Cypress microcontrollers, they're really cool. And it's something worth to, let's say, investigate and get familiar even more. But it was really like very easy to kickstart and move the things from ground up, really from scratch. So that's 2 main things. I made one last thing. It's also virtual collaboration. We also, I think, learn a lot. It says 11 hours on Skype, how to share the data, how to write the code in separate setups and communicate. So that was also very, even with like 1 year already in this virtual world, this still was a very big learning.
I have a question from Siegfried, one of our most important mentors at Infineon. He asks, it would be a great story to have this working also for any control like gaming. To my knowledge, in EEG, the neuronal currents are overlaid from the voltages driving the muscles. Any idea on the feasibility?
Yeah, so at least from what we learned in this last 2-3 days, let's say, it's very easy to overlay those signals. So they're very, very weak. We're talking about like microvolts, 10 microvolts of range. It's like factor of 10 weaker than ECG, for example. And even like eye movement would be like creating spikes, what people call artifacts, which basically ruins your recognition, like pattern recognition. And that's why if you do an ECG, like an EEG test, you have to be calm and sit and don't move much. So here, like 2 aspects. One thing is more electrode helps. So for example, for gaming, especially when you have like a dynamic environment where you have to move eyes and so on, you have possibly more electrodes. So I know like companies like Valve works on the BCI, on the virtual reality helmet, but they have like a stripe around the head and the top of your head. So you have a bunch of electrodes and that helps. And another thing, it's also like feedback. So in case of IR glasses, what we can think, you can stimulate the brain. So for example, you display something, and then to this, it creates again some activity in the brain, and this can be read by the circuitry. So it's, again, you have a peak in the activity, which is easier to spot. And there's also techniques where you stimulate the brain and then you make a readout. So you might kind of, if you take IR glasses, there's something flashes in the IR glasses, appears some kind of arrow object, and then depends on your processing, then you like accept action or decline action, or whatever you do, something like that. So, and also like if you have only like 2 classes, it's not like in the game that you have to move forever ahead, but you just like yes or no, or like left or right, that also helps.
Okay, so I have a final question for you because we talked upfront before the hackathon, and you said, well, that might be interesting working with Cypress the first time. So from your side, as Infineon acquired Cypress last year, and we're working now with our colleagues from Cypress internally, like a new company, a new team together. What assets does Cypress portfolio bring to Infineon? What do you really appreciate?
I would say it's really a good thing, because as soon as I open this PSOC family and I play with as a PSOC creator and I spend with it like 10 minutes, I said, oh, well, good that Infineon bought this thing. Yeah, because it's really nice, and I think, as you can say, state of the art, where you can modify like analog and digital, so really mixed signal environment. And what you see in our case is true mixed signal setup. We have analog front end, we have digital processing, and it's really in one bench. You draw it, and that's really handy. And also like all other things they have in this portfolio for the Bluetooth and Wi-Fi, that's really stacks up to a huge, strong portfolio in Infineon, like sensors and like actuators, power MOSFETs, and those things. So it's really, really nice.
Okay, so thank you, Sergey. Thank you for your wonderful contribution. And then greetings to the team. And then I would like to continue with the final pitch with Dejan from Serbia. Thank you, Sergey. Dejan, please, you're welcome here.
Hello.
Yeah, and I'm very happy that you joined, because actually, as far as I understood, the hardware arrived just in time in Serbia. I think you got it on Monday.
Yeah, it was just in time.
Just in time. So
yeah,
I can assure you everything was planned right away. That is just in time.
Yeah, so we cannot get hardware before.
Yeah, so it was
work upfront.
Fate was helping us that you could participate. So I would say, Dejan, the floor is yours, and please start your presentation. Thank you.
Thank you. Sorry, it's dark around me. It's because the previous presenter was talking all the time. Okay, Google, turn off lights. Okay, so my home reacted as well. So BitGear team, let me share the presentation. First, it's very interesting that I'm by far the oldest one of the presenters. So it is because BitGear, my company, we are actually a professional organization and so on. So we just wanted to participate a little bit in hackathons to see how it goes. Let me share the presentation. Okay. So I don't know if you see it. Hello, I cannot hear you, Rafael, by the way. Yeah.
I see the presentation. It's perfect. Just continue. Thank you.
Okay. So biosensing track. Okay. So why hackathon at the first place? So we are like a product development company. We have like 40 people. So we do this every day. What we did for hackathon. The idea was to get, let's say, hold on Infineon solutions and chips and to see how they work. And it was a good chance for us to make us do that, to inspire us do that. And also we wanted to have a little bit of fun and to give it a try a little bit in this hackathon stuff. So why actually biosensing track? It is because we are expert in acquisition, processing, and actually getting information from biosensing biosignals. So we worked a lot with different types of these signals. For example, ECG, EEG. Sergey said we have a lot of experience, so he can ask us how to improve the design if you wish. These technologies, they become pervasive in all industries, and also if you see the acquisitions of the companies as well, they are trending in that direction. first the team, it was presented, it was represented by two guys, Stefan and Milos. However, many people joined, in a ad hoc way. So many people from let's say with different skills, they were taking a little bit of part. They were taking a little bit of small part of this session. Our project actually, because we wanted to try how, because we like to acquire signals and to let's say to understand better how they can be applied in the realistic scenarios, like when bodies moving or whatever. So we selected to let's say to make a system which would acquire EMG signals. It's actually a muscle noise. So when you move, it creates a noise. And usually it's considered to be not so good thing when you are acquiring ECG or EEG. However, muscle signals can be used in a very, very interesting ways. The point of the project, actually the scope, sorry, of the project also included a pre-processing of the EMG signal and let's say detecting the specific events and their properties, and also reading a temperature and sending it to let's say to the mobile application just to wrap up it as like a sensor node, to put it that way. So use cases is everything associated with use cases are everything associated with muscle activity. So, for example, fitness. Also, there are activities in, let's say, medical, in medical space. For example, detecting if somebody, doing some involuntary, let's say, chewing during the night, or let's say for dentists to determine like what is the chewing power or whatever. Like all these things which are associated with let's say engaging the muscles can be let's say treated with this type of processing. So system design was to use all what you provided on Monday, so that was our system design approach. And sorry, okay. So this is our setup actually, and this is the setup of the front end of the system on chip device. Very nice device, by the way. So the feedback is very positive, to put it that way, and also it performs well. It takes a little bit of time to make it work perfectly, but that's what we do for a living, basically. And it's very pleasant to work and very pleasant to let's say to configure. So we are going to use this system on chip from now on. So you will have a lot of revenues from our devices which have your chips inside. These are the outputs. Let's say this is detected the EMG signal and also pre-processed with the let's say envelope detection. So for some reason the resolution is not very well, but what you saw on the scope in the previous slide, it happens here. So where you were like pumping a biceps, it reflects as a noise of the muscles. So temperature is just forwarded as like to the customized example of the let's say available firmware and mobile application. And summary. So what we didn't finish and we wanted is that when you get this envelope, to let's say to characterize it a little bit, so you don't send just an envelope, you send also like some data out of it, like what is the power of the muscle contraction, like what is the duration, what is the agility, and so on and so on. But we didn't have a time. We haven't spent let's say all 48 hours in the office, to be honest, because we are like it was mostly like a 10 hours, I would say, a day, not too much. But anyway, in order to let's say to acquire signals and to really like set it up to work with the practical applications and with the probes and so on, so to get to get signal nicely acquired. It took some time, and it took definitely a lot of experience in acquiring these signals. Summary: we got familiar with the technology in some kind of crash course manner. So we got this impulse to try the new technology, and also the conclusion, as I said, is this is like a very useful piece of machinery. Your chips are very nice. So that was from our side, like a wrap up.
Okay, thank you very much, Dejan. It was really a pleasure watching at your presentation. Thank you that you even took time. I'm sure you have enough business on your side, priorities you have to do. So thank you for participating in the hackathon.
I'm pitching, not my colleagues, because they said like, okay, you applied for the hackathon, now you pitch. Here you are.
Okay.
So we did the hard work now, and I'm doing this like administration stuff.
Yeah. No, that's really wonderful. So what I'm interested in is perhaps what many people don't know, the Vienna sales office at Infineon is also responsible for Southeastern Europe. So we actually kind of related and have a great colleague here in Vienna who also travels around these countries. What about perhaps a general question about your country and your region, as I don't really know it? What about the tech scene? You know, what's going on there?
Yeah, so in terms of let's say Belgrade, Serbia is first. It's not very far away from Vienna, by the way. So we are neighbors, basically. It's like I can, let's say, start from here at 7 a.m. and be on coffee in Vienna by noon. Belgrade is has a lot of traditional electronics. And we have several companies which are doing the electronic stuff in a kind of different way and different manner. So in terms of, let's say, R&D, BitGear is a little bit specific because we are doing also solutions for IoT. It's not just like electronic stuff, but it's more like application of electronics in a more broader sense, in a let's say digital transformation solutions based on IoT. You have everything in Belgrade. Belgrade is really like electronics center. Maybe it is not very well known, but that's how it is. So, Infineon is very welcome here as well.
Wonderful. Thank you, especially for participating and for
it was
taking the initiative. And perhaps another question about the challenge. What was like the most difficult thing in this challenge?
Yeah, but the most difficult thing is like when you attach the probes and there is nothing out of it, So it's normal. Like it's to set up the acquisition. It's like a normal process. It went quite straightforward with your technology. But basically, that's just the beginning of the application itself, because the understanding of like a final use case and let's say the use case scenarios, like do people move, how to acquire the signals, and so on, so on. This is just like a beginning, like a foundation, just to extract some nice signals, show them, and to inspire the application based on like a muscular noise, muscular signals.
Okay, yeah, very interesting. What do you see as a next generation application for biosensing? What are the growth areas? What do you think could be possible?
Yeah, there are like these electro signals, both EEG, EMG, ECG. That's more or less the same, let's say, technology. Then I would say like optical signals as well from biosensing for biosensing. And also like motion signals and so on, so converging into some kind of like a nodes for wearables and so on. So that's something which, obviously becomes pervasive, and that's the future.
Okay, that's the future. That were the last words of our hackathon teams. They are the future. And I'm also sure that our listeners are the future. So thank you, Dejan, directly from Serbia to Vienna to the whole EIT manufacturing and Infineon community. Thank you so much. And I want my regards to the whole team. So to sum it up, we had 10 teams. First one from India, Avijit and Deblina with the team Iris. Then we had Mohammed from Iraq, last minute participant who did an amazing job. We had Tobias, who worked 2 days in the background, who also did a lot of innovation. Then at the soundtrack, we had the Spartans of Machine. We managed that as well. We had iBreath, Statis from Greece, and Saria. We had Identify with their team, and with the 3D track, we had one team, and they really pioneered it. Also, a collaboration with Theowien, with Professor Schlund, the team from Infineon. Thanks also for that. And finally, the biosensing track together from 200 meters, but due to restrictions, really the Convival team, Martin and Aaron, Midnight programmer Sergey and his colleagues, and finally Bitkier from Deon. And the last thing I want to mention, and I'm really happy about that, we had teams from 9 countries: Austria, Germany, Greece, India, Indonesia, Iraq, Pakistan, Serbia, and the Ukraine. So I'm really happy about that, a sign of international collaboration and peace. So that are my final words. Thank you, and I hope to see you at the Hackathon Awards and the program. And so I would like to give back to the studio. Thank you.
Thank you so much, Raphael. What a great moderation. Thank you so much for leading us through those great pitches and for adding to the internationality of this manufacturing days.